requiring me to remember to hit record at the beginning and hit stop record at the end. So I'll screw it up at least once. So that's the idea. So we'll be studying the real numbers. And maybe a good follow-up question is, what are the real numbers? Sure.
I'm going to go with previous answer. Anything that is not related to I.
Anything not related to I. It's not a terrible answer. But let's see, how many people have taken like an abstract algebra class? Cool. How about linear algebra? What do you call a matrix with the real number entries of a real number? Probably not. It's a matrix. So we'll build a concrete answer to what the real numbers are, and they will exclude I. And that's something that we'll get to by the end of week 2. What are the real numbers? Before we can do any of that, we'll need the language upon which all of mathematics is built, namely set theory. So the course of these first few lectures is the development of what's called naive set theory. We won't try to be rigorous or justify the abstract fundamentals of what set theory is. If you want to do that, there are lots of good resources, some of which I would be willing to say would make a decent directed study if you're interested in that kind of thing at some point, on the so-called Zermelo-Frankenel axioms of set theory. And there are a few references there. There are also a few good open source textbooks if you even just want to prowl around the internet and find something without committing to buying a textbook. Cool. Let's talk about the syllabus. And since I've handed out all the copies of the syllabus that I printed, let's even talk about where to find all of the material online for this class. So you'll see on the syllabus a web page. And that web page can either be remembered as a URL, but who remembers URLs nowadays? That's probably good enough to find me. So there's my web page. Here is the web page for the course real analysis, whereupon you can find an online version of the syllabus. So maybe textbook first. The official textbook for the class is that green book, An Introduction to Analysis by Cornwood. Ever managed to score a copy of that from the bookstore? Okay. I won't reference it a whole lot. I certainly won't expect you to bring it to class because it's a little bit heavy. Some problems will be pulled from it. There will be some references to things in the book. Most of what I'll do will be self-contained within these notes, though. You know the meeting time, office hours. Oh, did people get an email from me earlier today saying something about office hours? Okay, and that email came through Canvas? Okay. Perfect. There will be office hours. Those are the times that they'll happen. I'll have them online. There's a link in Canvas, which hopefully everyone can get into now, right? Okay. If you can't in a day or two, we'll need to figure that out. Important deadlines. So let's see. Maybe the things worth highlighting is there's a description of the homework breakdown here. There will be some homeworks. There will be some exams. Maybe the things that aren't obvious what they mean. So there will be 3 midterms. And one of the things they'll be graded for is on a mastery basis. And what do I mean by that? So you'll take the midterm in class. That grade will be recorded. You'll then get an attempt to make a revision after I give you your graded midterm back. You'll mark that up. I'll give you a resulting midterm exam grade based on something. It's in the syllabus if you want to read about it. But then the additional thing I'll require is even after that, I'm going to make you continue to perform revisions on these midterms until you have 100% on that midterm. Once you have that 100%, you'll get that mastery point. That make sense? And then we'll talk about once it's time to talk about it again. There are challenge problems throughout the notes. And maybe a way of seeing them is if you look at the table of contents, which is included in there. There are a few items in there called challenge problems. So those are worth points in 2 different categories. Everyone will be required to complete a challenge problem. Once you complete it, you'll get whatever it said on the syllabus points-wise. The challenge problems will also count as extra credits. Each challenge problem will be worth a 1 percentage point bonus on your final semester grade. As a consequence, it has happened in the past that someone in this class has scored like 115%. I don't expect that to happen. That was only one person has gotten over 100% in the class, and it was this person who got 115% in the class. So there's lots of extra credits. You should take advantage of them. In particular, you have to take advantage of at least one of them. How you will complete those challenge problems, which is in the syllabus, is you will present them to me. So you'll come by my office. You'll talk me through the content of that challenge problem. At the end of your presentation, I'll say, well, I'm unhappy about this, this, and this. You'll get half credit on the challenge problem for now. Go fix those and come back and present to me again. Possibly later that same day, possibly later on in the semester. Any questions about things so far? Any questions about, like, when I want challenge problems to be done by? Yeah.
What is the specifics on when you want them done by? Is it at any point? Or?
Yeah, the deadline for any of the challenge problems is when I go home on the last day of the semester before final exam week. Don't put it off till then, because there are possibly 17 of you in this room. If all 17 of you show up at like 3:30 on the last day of class, at most 2 of you are going to present. Groovy. And I don't intend people to ever get all the points the first time they present. And if you're presenting on the last day of class, it's not going to be a second time. Groovy. There will be a final project. We'll talk about that, I think, closer to the end. Closer to when the final project is relevant. Any questions about grading right now? Groovy. I guess let's talk about homework deadlines. Oh, let's see. Face masks, everyone's wearing one, good. If I need to go online, we need to go online. If like lots of people are quarantining or I have to quarantine, I'll switch to an online format. I won't be happy about it, but that's okay. You probably won't either. Seating, I already said some stuff. Try to stick with your current seats. All right, only so the last thing that I'll mention, the rest of it, maybe I'll ask that you read through the syllabus and see what things you have questions about. Oh, no, 2 things. The homework will be officially due 1 week from the day it's assigned. So the stuff assigned today will be due Monday of next week. So there's the official deadline. I will accept the homework up until the moment that I start grading the homework, which will be sometime after that. So like if Sunday night rolls around and you're working hard on a problem and you know you're not going to get it done by midnight, send me an email and let me know the situation. I'm flexible with homework deadlines, but communicate. Groovy. And maybe the last thing is accommodations. So if you have a visa through the Students with Disabilities office, show it to me sometime soon. Come by my office and we'll talk about what the accommodations are. If you have accommodation through the languages department, come see me, and if I think the standard accommodation there is time and a half on exams, which you're entitled to if you want. Cool. So those questions? Yeah.
Are homework just submitted through Canvas?
Yes. Yeah, so on Canvas there will be places to submit. So let's actually maybe say, like, what are the homeworks going to look like? So maybe I'll go ahead and show you what this day's homework is. These problems, one of which is just, do you understand the set theory operations? The other ones are asking you to actually prove some stuff. And so what I'll have you do is you'll either write up your proofs by hand if you have good handwriting. I have to read it, so it better be readable. Or how many people have heard of the typesetting software called LaTeX at some point? How many people have used it at some point? How many people would like to continue using it during the course of the semester, during to collect their homework? Oh, cool. Yeah, you're welcome to do so. If you like, I've even on the course webpage given you a template for using LaTeX for the homework. So here I've given you a text file, which is a template. I'll suggest if you want to, using overleaf is the easiest way to go about that. Nice. If you want to use this semester as a chance to learn to use LaTeX, it's a nice way to typeset mathematics. It's what I use to generate all the notes in this class. This is a good way to do so. Try to do some of the homework using it. I won't require it, but. Cool. I think I'm about done with the logistical stuff. Any logistical questions before I start talking some math? Cool. So one thing that you'll find during the course of this class is I'm bad at starting things. This has felt quite awkward. And I'm even worse at ending things. So, I guess it's awkward. There's the screen, so you guys are looking there, but the clock's there. So you won't know if I'm going over unless you keep looking back. Except there's a clock on the screen, too. So, naive set theory. Let's talk about some set theory. So, what is a set? Yeah.
Collection of things.
Yeah, great. And that's going to be a perfectly adequate definition for us. I said I'm doing naive set theory. If I were doing rigorous set theory, I would say I'm not going to define a set. Here are the abstract properties that sets satisfy. And if you want to be rigorous whenever you do mathematics, you have to build everything axiomatically. And to do that, the Zermelo-Frankenel axioms are the path. But for now, a collection of things. There will be a symbol that will be used an awful lot in these notes. That symbol. How many people have seen that symbol? / how do you read that symbol? What does that say? How would you read that? Sure. Right. If a set is a collection of things, is a set. Saying X is an element of A means X is one of those things that are in the set A. Nice. And I'm going to do that so it stops jumping out of focus. So, some more just language. What is that symbol? How should you read that? Yeah.
A is a subset of B, or A is a subset of B.
Yeah, great. More formally, what does that mean? What does it mean to be a subset of another set? Yeah.
All elements of A are contained in
Nice. All right, so we're going to prove lots of things in this class. And a lot of the things that we'll be proving are that some set is contained in some other set. Well, so how would you prove that? You want to prove that every element of one set is contained in another set. So I guess to do that, you should consider any element of the smaller set and then show it's in the bigger set. Cool. So we'll see how pacing feels. So here is a claim. The open interval from 0 to 1 is a subset of the closed interval from 0 to 2. Now I'll give you guys a choice. Should we spend time talking through exactly that too? Do people like that? Okay, then I will not. Right, it should be something straightforward. Consider anything in this set. You want to conclude that that thing is in the closed interval from 0 to 2. Figure out how to go from one to the other. Cool. equality. What does it mean to say that two sets are equal? What do you think it should mean? Yeah.
To me, it seems like every element in set A is equal to every element in set B.
So I'm going to write that, and then maybe I will massage this sentence a little bit. Maybe I'll object to that just a bit. So here are two sets that we'll go through the argument why they're equal. Negative 1, 1 is equal to the set of all x's such that x squared is equal to 1. Right, that seems true, right? Let's parse out what this says. So 1 is a thing in that set. And so I guess that means that since this 1 is an element of A, that 1 had better be equal to absolutely every element in the second set. Is 1 equal to 1 and equal to negative 1? Nah, so I'll object to that language just a little bit, but that's clearly not what you meant. What you meant somehow is that, like, the elements of A are exactly the same as the elements of B. And right, that's what set equality should mean. They contain exactly the same things. So I guess that should mean everything in A should also be a thing in B. And also everything in B should be a thing in A. Does that achieve the desired result? There's what I'll mean by set equality. Two sets are equal if A is a subset of B and B is a subset of A. So far, so good? Hopefully also stuff that feels pretty familiar from, at a minimum, linear algebra. Or maybe I'll also gauge what classes people are taking. So everyone should have taken linear algebra. So maybe I shouldn't even. Has anyone not taken linear algebra or equivalent? Okay, we'll talk at the end. It sounds like it's a complicated, that's all. How about the class on discrete mathematics? Okay, cool. That's a good class for background and influence. How many people have taken abstract algebra? All right, awesome. So I'll expect even better proofs out of you. I'll grade you uniform instead of one. So, let's prove a set equality statement. So let's show that the set containing 1 and negative 1 is equal to the set containing all x's such that x squared is equal to 1, where this is like a bit of notation, right? Whenever you see something like that, you should read this as the set containing, spelling is hard, pretty sure that's wrong, all x's such that x squared equals 1. So that's so-called set builder notation. So let's prove that these two sets are equal. So that means we need to show that each one is a subset of the other. So I guess that's like really two proofs we need to make. So, I don't know, maybe I'll see how people feel. Do people want to take the effort of talking through either of the proofs needed to do this? Does anyone feel like that would be a useful bit of recollection? Okay, yeah, well, let's do it. And we'll do at least one. We have two things to prove. We will need to prove this, and we will need to prove that. And they're written in this order, but not for any particular reason. Which one would people like to do first? People who have a preference for doing the first one first? Anyone have a preference for doing the second one first? Fair enough. So, let's show that the set containing 1 and negative 1 is contained in the set of all x's whose square is equal to 1. So here's what I'll do. I'll start by considering any element of negative 1, 1. I've called it A just because, like, the symbol x already kind of has a job. Does it matter what you call that thing, though? You know, I mean, as long as it's consistent throughout and you don't use the same variable for two different things, This isn't computer science. I'm not going to demand meaningful variable names. All right, so A is in the set containing 1 and negative 1. So what might A be equal to? 1 or negative 1? All right, so that sounds like we have a case-by-case situation. A is either 1 or A is negative 1. And let's think about what we need to show. I need to show that A is in that set. Well, things in that set are things whose squares are 1. So I need to get the square of A to be equal to 1. Oh, hey, is that like obvious in each case? Well, I guess approximately obvious? Well, assuming some things about algebra, which I'll allow us to assume now, we'll discuss rigorously later. In the first case, that A is 1, then A squared is 1 squared. And what is the square of 1? 1. Right, we'll discuss why 1 times 1 should be 1 soon. In the second case, then A squared is negative 1 squared. And what's the square of negative 1? 1. Cool. In either way, did we get A squared to be 1? Oh, hey, but that means that A is in the set of all things whose square is 1. That completes the proof of one of the directions. Is that pretty straightforward? Let's go the other way. And we'll assume more algebra that we'll justify later. So suppose A is in the set of all things whose square is 1. If A is in the set of all things whose square is 1, then what can you tell me about the square of A?
It's 1.
Yeah, it's 1, right? A is in the set of all things whose square is 1. That means that A squared is equal to 1. That's how you should read set builder notation. Telling you that A is in the set of all x's which satisfies some statement means A satisfies that statement. So there's the bit of algebra that I'm going to be non-rigorous about. What are the solutions to the equation A squared equals 1? Yeah.
Plus or minus the square root.
Plus or minus the square root of 1, and the square root of 1 is what? Yeah. So A is a solution to this equation. The solutions are that. So A is either 1 or negative 1. How did that feel? Good enough? Groovy. So let's talk some more about set theory, some more operations and proving things with sets. Okay, yeah, concluding sentence. As we've proven that this set is contained in that set, and that set is contained in this set, we conclude that the two sets are equal. Right? That's a sentence that's important to write down. You should write down what you've proven, and not just say the proof is done and count on the reader to believe you. Nice. So we'll use that kind of language a lot. So if A is some big set and P is a statement, then saying the set of all x's such that P of x. How do you read that? That is, well, I guess I just said it. That is the set of all x value, x in A, such that P of x is true. And there I put that last sentence, is true, in red, because often when you would write the set of all odd numbers, you wouldn't say the set of all x's such that x is equal to 2k plus 1 plus some k is true. So it's in red because you would often leave it out. But for emphasis, it's the statement. For example, if you want the set of all positive numbers, well, that's a set of all x's such that x is bigger than 0. People feel pretty good? Groovy. So, yeah, let's go right down here. Let's talk about intersection, union, disjointness. So, again, intersection, A/cat, if you want the type, B. What is that set? I'll give you two sets and ask for their intersection. What am I asking you for?
they have in common.
Yeah, the elements they have in common. So maybe I'll write it informally. The elements A and B have in common. Put quotes around it because that's some slightly informal language. Let's say it in set builder notation. So what does it mean to be in A intersecting B? That means you want things that are in A and in B? Oh, hey, that's a set builder kind of thing to say. So let's put that in set builder language. There's a set of all x's such that x is in A and x is in B. That make sense? All right, what about union? What is the union of two sets given by? Sure.
All the elements contained within both A and B, but not necessarily in both. Just the elements that it's the elements in both A and B, not necessarily having to be both within A and B, but can be within both A and B.
Yeah.
That's wrong.
So the word you're missing that you're looking for is the word or.
Yeah.
Yeah.
That's the word I'm missing. Yeah.
Set of all x's such that x is in A or x is in B, or there's some subtlety. So maybe we'll do like a Venn diagram-y kind of thing. So if your sets A and B happen to be like circles, those are circles, then here's the intersection. There is the union. Everyone feel pretty good right now? So let's take apart that word or. So in particular, whenever a mathematician or a computer scientist for that matter says the word or, they're implicitly allowing for both things to be true. So the subtlety here is, if you have two statements P and Q, P or Q means that P is true, and that's like a silly thing to say, or Q is true, and then for emphasis, or both. But I want to include things that are in both A and in B in the union, not just things that are exactly. Everyone feel pretty good? We say two sets are disjoint if. Well, what does it mean to us? That's, yeah.
Sorry, backing up a little. So that's an inclusive or for that statement.
Yes. Or is the inclusive or for a mathematician.
Okay.
If you're a computer scientist, then maybe you would say like XOR if you want to do the exclusive or. I'll encourage you not to use that phraseology in mathematics, though. Instead, just say what you mean. This is true, or that is true, but not both. Cool. Let's talk about disjointness. So let's take exactly that picture. So those two sets A and B, would you call those two sets disjoint? Would you want to call those two sets disjoint? Why not? They share elements. There are things in common. So we'll call two sets disjoint if, informally, they have no elements in common. That is, if they have stuff that's in the intersection, then I wouldn't want to call those two sets disjoint. So the more rigorous way I'll say that is if A intersect B has no elements, I'll call A and B disjoint. So if A and B is the empty set, then I'll say that A and B are disjoint where the empty set, or sometimes the set containing no elements, either of those denote the set which contains no elements. I'll usually use the symbol to the left, but hopefully it's also clear that the symbol to the right, you would read that as the set which has nothing in it. Cool. Nice. All right, so we have some of this language. Let's prove some things. Let's prove something about intervals and their intersection. Again, this is another just toy example. The actual argument will be easy. The thing I want to emphasize is the language of the argument comes. So, here's a claim. The closed interval from 0 to 2 intersected with the closed interval from 1 to 3 is equal to the closed interval from 1 to 2. I guess first things first, do you believe that that's true? Yeah, right. Maybe the picture is like there's the interval from 0 to 2. There's the interval from 1 to 3. I want things that are in both of them simultaneously. So yeah, that's 1 to 2. It seems reasonable. That picture is not the proof, though. Let's see. There are some things to pick apart here. You want to show the two sets are equal. How do you show the two sets are equal? You prove two set containers. So, there are two things what need to happen. We will need to show that the intersection is contained in the interval from 1 to 2, and show that the interval from 1 to 2 is contained in the intersection. So what do you think, everyone? So seeing those two statements, do you have a feel like you know how you would go about proving? People feel pretty good about those? Alright, so here is what I think seems like an excellent idea. Let's take advantage of the fact that there are at least two people at every table. Pick one of these two claims, one of those two steps, and complete that step. Either doing the fill in the blank thing or coming up with your argument on your own. We're trying to figure out how that proof would go. If anyone here is really a big fan of how pens look instead of pencils, but also likes erasing, I can recommend at least one brand of erasable pen.
Really? All ones that ever tried stuff.
I mean, this one looks okay, right? This is fiction. But this is a distraction. Stay on top.
Okay. So this is my first time thought about the first in a while, so somebody out of my mind here. But I don't know if that's actually
people feel about one of the two arguments? People feel ready to talk to one of them? So let's talk through this first one that has like the gaps, and then we'll like sketch an argument on the board, and then we'll probably be pretty close to time. So let's suppose you want to show that this intersection is contained in the interval from 1 to 2. Well, then the way the argument should go is you need to start by considering anything in the set that's allegedly smaller, and the eventual goal has to be that x is in the interval from 1 to 2. So, when in doubt, the first attempt at an argument is often just like massage the statements around and see if you can like get them to line up correctly. So x is in that intersection. What does it mean to be in the intersection of two sets? Yeah.
It means the elements are contained, the section of the elements you're looking at is contained in both sets.
Yeah. So this x has to be in both of the sets. So here are like two statements. Right. There's a statement which we know is true. There's another statement we know is true. Let's see what these two statements mean. X is in. I know it has that on the previous line, but I'm going to put it here too. As x is in the interval from 0 to 2, what can you tell me about x? What does it mean to be in the interval from 0 to 2? Yeah. Awesome. Hopefully everyone knew that already. Okay. Excellent. Well, we also know that x is in the interval from 1 to 3. So that means I know that 1 is less than or equal to x is less than or equal to 3. And there's the goal. X is in the interval from 1 to 2, so it looks like I need 1 is less than or equal to x, and x is less than or equal to 2. Have I already stated somewhere that 1 is less than or equal to x? Yeah, right? Right there. 1 is less than or equal to x. Since 1 is less than or equal to x, have I also already stated that x is less than or equal to 2 somewhere? Oh, neat. So the statements lined up. Does that feel pretty okay? So a lot of, well, some proofs of set equality will follow exactly writing down the definition of one set, writing down the definition of the other, and trying to get them to line up correctly. And let's see, I won't try to do the other direction on paper. Maybe I'll go to the board and we'll try to just sketch out the thing. We'll write down the things that we have, and we'll try to figure out how to get the thing that we want. So, let's sketch it out. I know this board is like super beat up, but is it readable? Okay. So let's try to show that this interval is contained in that intersection. So, let's consider any x in the interval from 1 to 2. What does it mean to be in the interval from 1 to 2?
That your value is equal to or greater than 1, but less than or equal to 2.
And let's come at it from the bottom as well. So there's the thing that I would like to show. This is just going to be a sketch, so I'm not going to try to insult any of the rules yet. That was kind of what I actually write it for. If I want to show x is in this intersection, what do I need to show? What does it mean to be in the intersection?
Then you have to prove there's some amount of x that exists in both sets.
Leave out some of those rules. You need to show that x is in both sets.
Okay.
Yeah, x is a number. I don't know what some amount of a number is.
Okay.
So, so I need to show two statements. And I'm putting these full arrows and hope that like I can eventually get there. Well, what would it mean for x to be in the interval from 0 to 2? Yeah.
0 is less than or equal to x, less than or equal to 2.
need to go from this to those two inequalities. In fact, how about this? Here are two inequalities. There are four inequalities. Let's just try to get one of them at a time. Given this statement, how would you show that 0 is less than or equal to x? Yeah.
We could say that 0 is less than or equal to our x, which is less than or equal to our the 2, because our x is considered to be 1, 2, the set of 1 and 2.
It's between 1 and 2. Let's focus on this.
Sorry.
Okay. So x is at least as big as 1. Does it follow that x is at least as big as 0?
Yeah.
Yeah, why?
1 is greater than 0.
1 is bigger than 0. So let's put that into laws. So that doesn't seem true. All right, so now let's go to less than or equal to 2. Why is x, if I tell you this is true, why is x less than or equal to 2? And this is like a stupidness, all right? Yeah.
By the supposition.
Yeah. By supposition, it's written down literally right there, x is less than or equal to 2. Do you think getting that statement will be more or less the same as what we just did? Yeah, great. So I'm not going to write that because I'm just about out of time. What do people think? Given this bit of scratch off, do you think you could put that argument into law? Groovy. So I'm going to go up to my office and consider the amount of election that I actually made into it, and from there decide which of the problems I actually want to associate with today, as opposed to, I guess, Wednesday. So deadlines might be pushed on. People feel good?
So is it going to be like, we're going to have like a couple of problems assigned for today, and then...
Yeah, check Canvas. Maybe I'll push the whole deadline back like it was all assigned on Wednesday.
Okay.
Maybe I'll say, wow, you have enough information to do like this one, so do this one, and maybe that one.
Okay.
Ideally, all of the stuff very much like review and background stuff, right? So, I don't think it would be unfair for me to say, you know everything you need to do all of the problems already. But we'll still talk a little bit more on Wednesday. Cool. So, we're on time. I'm going to continue standing here. So like I said, I'm absolutely terrible at ending things. So you should be packing and getting ready to leave, and maybe even leaving. I'm going to be here until I leave if anyone has any questions. There's another tour, so I'll be here until I leave. And maybe as people are leaving, was my spoken word and handwriting understandable? Was it possible to understand what I was saying?
Yeah.
Okay, and what I was writing?
Yeah.
Okay, excellent. There will be times when it isn't possible to read what I've written, and then you should just stop me.
Thank you.
Oh yeah, just like you waved your hand about whether you've taken it on your algebra. So what sort of class have you taken?
So I'm a transfer student. So I took linear algebra like 2.5 years ago.
Okay.
And it was very much an application class. We didn't do proofs
Okay.
very much. So yeah,
Okay.
my period was like really weak when it comes to linear algebra.
Okay. Have you taken another class where you use like blueprints and stuff?
Yeah, I took abstract algebra like a year ago.
Oh, then you're fine. Yeah, you're good. Yeah.
Would you transfer?
Malaysia.
Oh.
So yeah, I'm from.
taken a class at some point which spent some time on food lighting?
Yeah.
Oh, yeah. Which class? Oh, yeah, go home. Yeah. You're better off than linear algebra spends like a month and a half on this. Yeah. Yeah.
First, nice to meet you. I know I've seen you around a ton, but I've been here for 3.5 years. That happens. But I'm a very visual thinker, so sometimes I struggle to really articulate prompts. I literally forgot the word "or."
Oh yeah, that wasn't meant as a criticism.
No.
Yeah.
I took it as good. At least I kind of knew what I was talking about.
Yeah.
But for some reason, I do that kind of thing where